like to do another symmetric circuit, but in this case I want to do a little bit different slant. In this case, the currents are the inputs, and I have currents as the outputs. And so a lot of times we often see example problems that are voltages, but there's absolutely no reason that these can't be currents. So we're going to talk about a current example. And so this is now going to be a case of differential currents I1 and I2, and differential output currents IA and IB coming out of these two controlled current sources flowing out of this particular power supply. All right, so now we begin to ask the question, well, how do we begin to analyze this? And then how do we begin to solve it? Now, before we do that, some of you may be wondering, where does the structure come from? And this turns out to actually be a structure called a Norton amplifier. So you might actually imagine having a differential input current, I1 and I2, and you get a differential output current measured, IA and IB. And so many people are used to differential voltage in and differential voltage out. It's actually a current amplifier, and so it's actually called a Norton amplifier, much for the same reason that we talk about one-port equivalent circuits being a Norton current source. It all comes from the same structure. For those who are also familiar with transistor circuits, you might recognize this as sort of also a core component for a two-input case of what is typically called a winner-take-all structure. A similar idea. So then you begin to look at the circuit and you go, imagine I apply common and differential sort of inputs. And remember, I could take a particular input and always decompose it into the sum and the difference. And we'll look at that at the very end, just for clarity. But if I took the sum part of it, which would be, again, the whole circuit is linear, so I could take that part. Again, I could take the sum part and then take the difference part and analyze those separately and then add the results in a linear system. Again, superposition holds. I just picked a very interesting superposition. All right. So what happens when I put I1 and I2 as being the same current? Well, there's a point of symmetry and goes right down the middle here. That point of symmetry, by the way, notice that the R1 actually splits into two R1s in parallel. But in so doing, I can split right down the middle. There's open circuits there. And so I'm sort of left with half the circuit, which I could imagine could just be this half the circuit, which then we can just draw right down here. Here's half the circuit. And you notice that all the elements are still there, but we only have half of them. And so this is really gives us an opportunity to kind of solve this. Now, if I look at it for differential input currents, I1 and I2, it means that everything along that same line of symmetry now effectively goes to ground or goes to a fixed potential. And so the VA term goes to a fixed potential. VA going to fixed potential is kind of useful because it means this current source disappears, these two, as well as this one and this one. So that turns out to be quite helpful. And so what I'm left on the outside is just an R2 with the current source, and I have something out to a fixed potential. I just sort of kept the voltage source there. I could have also just removed it. Either way, kind of becomes sort of no real difference here in terms of how we're doing this. The differential mode is pretty easy because I get current to voltage, and that turns out to go in, and then I go from that voltage to basically current out. So I get a GM2 V1, and then I get R2, and that just gives me this sort of value of 100. Because GM2 is 100 over 100K. I have R2 is 1 mega ohm. The ratio of that is 100. So that works out really well. So on the common mode case, it's slightly more complicated, but certainly not too difficult because we have sort of the node V1 because we have an input current source. We also have a VA node in here to pay attention to, and then look at what is the final output current. Well, the final output current goes through these two nodes and then goes to the resistor, so I can just define it as VA over the 2RI, or 2R1. I know that this IC, just writing KCL this node, gives me these two terms, and then when I look at the one here, I can look at KCL this node. It gives me then the element of GM2, GS, and R1. Well, this one turns out to be useful because it allows me to then look at the relationship between V1 and VA. One thing I'll notice, given the relative sizes of these devices, and if you're familiar with transistors, you're thinking, okay, yeah, I probably already kind of knew that certain things are bigger than others. But what you end up finding is that GM2 V1 is one term. On the other side, it's 1 over 2 R1 and a GS term. The GS is going to be larger than the 1 over R1 term that's sitting in the feedback. So this just turns out to be a pretty straightforward relationship. There's sort of a factor of 2 between those two. That gets put into this equation, simplifies the IC down. That gets put into this relationship for VA and IC. That allows me to kind of solve. And I get that common current is equal to the original common current over 2 GM R1. So I get actually that level is a very, very small number. In fact, you would say I've got 5 mega ohms times 2 times GM1, which is 1 over a kilo ohm. So that gives me basically something that's basically 1/10 of 1,000. Is 1,000th. And so that gives me two numbers, and it's really pretty interesting in how different those values are. And just to give you a sense of what this would feel like, imagine if I had two input currents, one at 20.1 microamps and another one at 19.9 microamps. You go, well, okay. The common mode current out of that is 20 microamps. The difference current is 100 nanoamps. So that's a really, really tiny current given sort of the baseline of the currents that you're working with. And you're thinking, wow, and again, you try to think about what that would look like from a signal perspective. And this is what we often want to do in terms of amplifying things, but I don't want to amplify just what's always kind of common between them. Well, if you look at this, what I end up getting is I get that IA would then actually be the sum of the two of the common and the difference with their particular gain terms. And so I get, basically I get this 10 microamp times 100, which gives me 10 microamps. I get, then I'll also get the common current and times this level, which then give me 2 nanoamps. I actually wrote 1, but in the end it didn't matter here. And that's approximately 10 microamps. So it's really amazing to see what kind of things happen with this type of a circuit.